Hello, I'm Chris Athanas. I'm a KMP developer. Tech support said they're coming out Tuesday or Wednesday, one of the two. We'll see. I'm not holding my breath. We're going to continue on our journey of data structures, leaving off on 100 computer science concepts. I'm just going to blast at you and maybe stop and comment on a few of them. And which ones are like important and key, and which ones not. He gets it mostly right. So let's give him some props. Go over there, like and subscribe on his Fireship. He does really great breakdowns of stuff, and that's a dirty keyboard.
What's the first thing you should do when your code throws? What's the first thing you should do when your code throws an error? Obviously, you should change nothing and try to run it again a few times. If that
that's for sure. You actually in the beginning. That is a good, useful thing, just to prove that no, nothing changed. But sometimes it does. Sometimes unplugging it in, pushing it back in does work. It's weird. It's very strange, especially when you're getting deep in debugging. And you've changed some stuff. Try and run it. I don't know. Maybe it'll work.
doesn't work, you're going to need a computer science degree. The awesome thing about software engineering is that you can learn to code and get a high-paying job while literally having no idea how anything actually works.
That's what this is about.
It all just feels like magic, like a pilot driving a giant metal tube in the sky while knowing.
Yeah, if you just learn the syntax of some React framework library, you're going to be very, very frustrated. Very frustrated. But if you learn it this way, coming from the ground up, it's like, oh, okay, you guys are just doing the same old thing. It's always been done 1,000 times, but now you call it something else, a new name. Hey guys, let's call it something new. It'll be exactly the same as the old thing, but we're going to call it a new thing. Let's do that.
Nothing about aerodynamics. Welcome to Computer Science 101. In today's video, you'll learn the science behind the garbage code you've been writing by learning 101 different computer science terms and concepts.
Okay, it's not science. It's not a science. It's what he meant by it at the time when that the computer science term was coined. He meant more like organizational science. Like if there was a science around how to organize work, and it just happened to be we're applying this to the computer, because at the time, a computer didn't necessarily mean just the machines, because there's a whole bunch of types of machines, and computing had happened with people, long before the computer science became a thing. But as the machines came online, we were starting to bump up with these, how do we conceptualize all these little bits and pieces of data all over the place? And that's when we came up with this thing. So it's really not computers per se, because if we had another device that was digital that could do the same thing, we'd be using that. Like I said, if it was a ball of a xenon gas that we flashed with a X-ray laser, we would be using that. So it does not really, the silicon chips and the tubes and the relays doesn't really matter. But how we organize this work of binary data information and how it works in a system that's has time limitations on it, yeah, that's all useful stuff.
This is a computer. It's just a piece of tape that holds ones and zeros along with a device that can read and write to it. It's called a Turing machine, and in theory, it can compute anything, like the graphics in this video or the algorithm that recommended that you watch it. At the core of modern computers, we have...
Right, so the Turing machine is just that fetch, decode, execute loop. Except instead of just one tape and an eye, it is just one cell at a time. Same thing.
Have the central processing unit. If we crack it open, we find a piece of silicon that contains billions of tiny transistors, which are like microscopic on-off switches. The value at one of these switches is called a bit, and is the smallest piece of information a computer can use. However, one bit by itself is not very useful, so they come in a package of 8 called a byte. One byte can represent 256 different values, like all the characters that you type on your keyboard. In fact, when you type into your keyboard, the character produced is actually mapped to a binary value in a character encoding like ASCII or UTF-8. Binary.
So we're going to just kind of like go over the same information a few times. That's one of the things I did notice in some of the courses I went to. They wouldn't come back and revisit or have different voices revisit the same topic in different angles, because that's the only way I learn is like I have to hear it different times and then I have to try stuff out. We'll get into trying stuff here in a second, or in this course. So I hope you go back and watch these videos yourself and go try the exercises and think with it and mess with it, because that's the only way you're ever going to learn this stuff. You can't actually learn it from a book. And if you do, it'll be very fragile knowledge, right? It'll be deprecated in a year and you'll be like, oh, I need to learn a new library. It's like, well, if you learn this lower level stuff, you can just zip off to another one. It's like, okay, it's just the same as the other thing. All right.
is just a system for counting, like the base 10 system you normally use when counting on your fingers, but it only has two characters, 1 and 0. Humans have a hard time reading binary, so most often it's represented in a hexadecimal base 16 format, where 10 numbers and 6 letters can represent a 4-bit group called a nibble. As a developer, when you write code in a
nibble. So there's when you have two of these together, it's called a byte, like because the computer, like when this word byte came along, it was the first time they were going from like old-timey 16-bit word computers where 16, like each address is just 16 bits at a time. So they wanted to like, oh, we're doing something more smaller, more edgy, more crazy. We're crazy. So they called it a byte. So instead of taking a whole 16 bits at a time, it took 8 bits at a time. There was one that was doing like 12 and different lengths of a word, what they call the word length, which is like the amount of data that's the amount of bits that are each address points to, or can the CPU can take at a time, or eat at a time, consume at a time. Like it's eating. It's so silly. It's dumb.
programming
byte.
language,
They have a nibble. So a nibble's half a byte. Ooh, okay.
will eventually be converted into machine code, which is a binary format that can be decoded and executed by the CPU. What it doesn't do, though, is store data for your applications. For that, computers have random access memory, or RAM. It's like a neighborhood, and inside of every house lives a byte. Every location has a memory address, which the CPU can read and write to. You can think of the CPU and RAM as the brain of the computer. But in order for a computer to be useful, it needs to handle input and output. An input device might be the keyboard and mouse, while an output device might be your monitor. Luckily,
I have this keyboard. That's why I use it right now. It's so badass. I love the K2. Keychron K2. It's sick. I keep on looking at other keyboards, like trying to get a better one. Like, no, this is the one.
most developers don't need to worry about how this hardware fits together because we have operating system kernels like Linux, Mac, and Windows that control all hardware resources via device drivers. Now, to start hacking on the operating system, your first entry point is the shell, which is a program that exposes the operating system to the end user. It's called a shell because it wraps.
Right. So this is like a little program that you run that actually does the fetch decode cycles. You know, instead of doing it, you know, say you have a little prompt and you say, okay, run this, and then it just goes, runs the program in here, and then brings you back to the prompt again. Well, which program do you want to run now, sir?
The kernel. It takes a line of text as input and produces an output. This is called a command line interface. Not only can it connect to your own computer, but with the secure shell protocol, it can also connect to remote computers over a network. Now that you have access to the mainframe, it's time to pick a programming language, which is a tool that uses the abstraction principle to make computers practical to work with for humans by simplifying different systems layer by layer. Some languages like Python are interpreted. That means there's a program called an interpreter that will execute each line of code one by one. Other languages like C++ are compiled. They use a compiler to convert the entire program into machine code in advance before the CPU attempts to execute it. This results in an executable file that can be run by the operating system without any extra dependencies. Now,
just a different kind of file. So the Python file has text in it that's interpreted or compiled right before it's run, right? So it takes that text and compiles it right before it runs, and then it runs the machine code. It doesn't actually run the interpreted stuff. It runs the actual machine code. So, and then C++ does, okay, we're just going to skip that whole interpreted part. We're going to compile everything ahead of time to all the machine code, and then it just runs that. That's it.
Now, every programming language has a variety of built-in data types to represent the data we're working with in our code. Instead of bytes, we work with more human-friendly things like characters and numbers. Now, the most fundamental way to use data in your application is to declare a variable. This attaches a name to a data point, allowing you to reuse it somewhere.
Name to a location in memory. So this just represents a location in memory that has this string of letters, string of characters, which is one memory location. Next one, 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 next thing, all the way to the end where it has a 0. Called null terminated string. Ooh, it's null terminated. Or you have a thing at the beginning. It says how long it is. This string is 22 characters long, or whatever number it is at the beginning. That's the other way. All right, that's more convenient, but it uses an extra byte. And back in the days when an extra byte or two meant a lot, and so they would put a 0 at the end. So it'll be a little slower to go through it to find, the computer to know where the end of the string is. But you save a byte. So that's where that came from. And that's why they did that. It's super goofy. I mean, we think now, but back then, memory was super expensive. When these computers came out with the byte memories, it was like $50,000 for like what we consider a toaster would have. A $50,000 toaster. And they're like, oh my God. That's what Unix was developed. This all the stuff that we're using here is all developed on those kind of machines.
Else in your code. Python is a dynamically typed language, which means we don't need to tell the program exactly which data type is assigned to a variable. It just figures it out automatically. However, other languages,
well, it does it by context.
Which means we don't need to tell the program exactly which data.
Right. How does it automatically do it? Well, if you have a quote at the beginning of this thing, it's probably, you have a quote at the end, probably going to be a string. If you have no quote, and there's no decimal, it's probably going to be an integer. No, come on.
Data type is assigned to a variable. It just figures it out automatically. However, other languages like C are statically typed, and that means you need to specify the data type of a variable in your code. When you
You're telling it, okay, even though I've got this quote here and it's obvious this is a string and it can't really be a number because there's no digits here, I'm still going to tell you that I'm intending this piece of data, the address that this string, this thing points to in memory, to have this in there as a character array. Array. This means a character array called hello that points to a string of characters. This in that, and put it in that array. Put that in the memory for me. And this is okay. Interpret this thing as an integer, not a float or character or a string of characters, but as an actual integer value, which that has no decimal point, and give it put it at this address, and I'll give it the name num, and that's all a variable is.
define a variable, its value is stored somewhere in memory on the hardware, and you may need to allocate and free up memory throughout the program. A pointer is a variable whose value is the memory address of another variable, which can be used for low-level memory control.
Yeah, it just points.
Many languages don't want to.
Points one thing to. So this address has a value. Okay, what address is it? Oh, it's this one. This other one over here, somewhere else in memory. Oh, a pointer.
To deal with low-level memory management, and instead implement a garbage collector, which automatically allocates and deallocates memory when an object is no longer referenced in the program.
Garbage day.
When I first heard the term garbage collector, I was like, what are you guys talking about? So when you go through and you allocate a bunch of memory, and like you say, I want this, I want this, I want this, and if you don't let go of it somehow after you use it, okay, I've used all that stuff up, I don't need it anymore. Well, it just kind of just stays there stuck. It says, oh, well, nobody said I don't need anybody. If it says that nobody else needs this plot of land, well, we're just going to keep it here then. And that's when it all fills up. If you're not taking it away, and if you're always allocating, well, eventually you're going to fill up the whole area. And like, well, I want to allocate some more. It's like, oh, no more memory left. Well, the memory's still there. It's allocated to something already, and you haven't let it go yet. You haven't done this. Like, okay, I don't need that part anymore. I don't need that part anymore. So it's just like not emptying your trash can. It's like, even though you're not in the program, may not be referencing those things or using those things anymore. If you haven't get rid of them, it was like a big problem when we had C. And then Java came along and said, we'll do that for you. And all you do is you allocate stuff, and it figures out if you're not using it anymore, and then lose again. Now, you can still make mistakes and still have this problem. So it's like you have to be aware of how these things operate. Under the hood, Java is notorious for it.
Now, the data types available are different in every programming language, but typically you'll find int to represent whole numbers, which may or may not be.
Well, the names of the types are different, right? What they call them, the actual character letters, each language, but they always have the same shit. They have an integer, they have a float, they have a character, they have a string. It's always the same stuff. They may slightly call it something different. Like in Kotlin, they call it data class or data object, and in other languages they call it a record. It's like, okay.
Be signed or unsigned to represent negative numbers as well. When numbers require a decimal point, they typically use the floating point type. It's called a float because there's only enough memory to represent a certain range of numbers at a certain precision, and is basically a form of scientific notation to make computers faster. If you need more range or precision, many languages also have a double that doubles the amount of memory used for the number. Now, when it comes to characters, you'll typically find the char data type to represent a single character, or more commonly, a string to represent multiple characters together. Ultimately, these characters get stored in a memory address somewhere.
Because they're strung along. So they call it a string, because you're like stringing along each character onto a string of beads of characters. That's really get the thing. It's a string. Why do you call it a string? Because they're strung along.
Somewhere, but they need to be stored in a certain order. When the order starts with the most significant byte in the smallest memory address, it's called.
Strings are always contiguous. It's very rarely you ever see a thing where they're not using it. Like one string is going to take up has to allocate all the memory for the whole long string. It's 1,000 characters, 10,000, 100,000 characters. It's going to allocate the whole thing. There's other ways of handling that, of course, but like that's normally how it's handled. So if you try and bring up a 20 megabyte file and you only have 8 megabytes of RAM or 4 megabytes of RAM, it's going to be thrashing the disk a lot.
Big endian, or vice versa, if the least significant byte is stored in the smallest address, it's called.
Right, this is important to know. So you have this little thing where, okay, so little endian and big endian. So here, so it's basically like, in what order the digits of like, if there's 4 bytes that make up one big 32 byte digit, does it go, is this the lowest value first, or is it the largest side first? Is it, which way is it going? Or is the singles digits over here, or the single digits over here? And yeah, that's what they mean by that. That's what they mean by that. And it's sad that he didn't reverse the numbers here, because they really need to be reversed. Like 01 should be here, 23 should be here. These should be back. They should be swapped. Boop. If we're little endian versus big endian. So that was a little flop in his part.
Smallest address, it's called little endian. When it comes to practical software engineering, one of the most fundamental things we do is organize data into data structures.
Yeah, endian. So which end is the big end? Is the big end on the front? Or is the big end on the front? Is the big digit on the front, or the big digit on the front? And on the end. Little endian, big endian. It's goofy.
The most useful data structure is probably the array, or list. Just like a shopping list, it organizes multiple data points in order. However, it also maintains an index of integers that starts at 0 and goes up for every new item in the list. That can be useful, but you don't actually need an index to create a list of items. Another option is a linked list, where each item has a pointer to the next item in front of it. Another option is a stack that
So they're starting to put these things together, like, oh, we can use this one for this, and this one's for this.
follows the last in, first out principle. It's like stacking a set of plates.
Now we have like one conceptual layer up. We got pointers and values. What can we do with those? We have arrays. We have arrays and pointers and values and variables. And okay, well, how can we put? Okay, we can make a stack out of it. We can make it simulate somebody in a line. We can stack where there's a pointer at the top. We can pop things off and on again. And I do want to point out that there is this really great playground for these types of things, and I'll leave links for this, of course. Let me clear this out. I was messing with it. So let's just so this is an array implementation. Here's the top pointer, which is pointing to the top array. And this is like a fixed array of 30 elements. So you push one on, it puts it right there. Let me slow down the animation here. Boop. Let me push the next one on. 55. Push. Zoop. Zoop. So it looks at number. So where's the next one? It's going to be on the top of the list is the next elements here. So sometimes the top means it'll point to this one. Sometimes top means where the next one's going to go. So you can play with this stuff and see how it works. And then they have, let's go back to the list of here. And they have like the linked list. So that was a stack. And then they have the same thing. Here's the linked list. Now this top points to this memory location. And this little node right here, so the value of the node is 66. This is called a node, and the pointer to the next node. All right, and then if you pop, what happens? Gets rid of it, and that's the pop value here. Pop it again. Pop value 66. So that's like so you can like visualize what the heck these people are talking about. And if you look at the code, which is always the same for this kind of stuff. And then you look at how this works, it makes it like super clear. Like, what is this going on here? Yeah, so that's what's going on there. And keep going.
Then when you want to access the data, you pop the last one off the top. The inverse option is a queue, which is first in, first out. Just like when you get into the breadline, the first person there is the first one to be fed. Now, another extremely useful data structure is the hash, which might also be called a map or dictionary. It's like an array, but instead of an index of integers, you define the keys that point to each individual item, giving you a collection of key value pairs.
Yeah, so I want to look up someone's name. Well, give me their phone number. So this is their name, their phone number, name, phone number, name, phone number, name, phone number. That's it. It's like if this was an array, like they do in JavaScript. This is a 0 is first one. 1 is the second one. 2 is the third one. 3 is the fourth one. That's it. Then people make a really big deal about this. It's just map. So all map is here's the key. The key is square. The value is some graphic or some object, some value in memory that represents what the square is. 4 numbers or something. Circle, it'll be a radius and diameter or whatever. And that's all it is.
In many cases, though, it's not efficient to organize data in a linear way. To address that problem, we have trees, which organize nodes together in a
right. It puts it upside down here because
to address that problem,
because computer science would put the tree upside down. We should call this like something else, like roots or something like that. But we don't call that. We just call it a tree. So you have to flip it.
when we have trees, which organize nodes.
And they're getting this terminology from the math people. So the math people are the ones that flip the tree upside down.
together in a hierarchy that can often be traversed more quickly. This can sometimes be too rigid of a data structure though, so instead a graph can be created to connect multiple nodes together in a virtually
Right. So this has just got two, right? A tree only has two nodes. Well, not really. I mean, if you're talking about real trees in the forest, no, they don't just have two. They have multiple branches. So it's not really a tree. It's like, okay, the mathematical. Okay, so you're talking about this specific tree, which actually has the same name as tree, but you're talking about something completely different. This mathematical concept, which is strictly one node, has only two branches. Okay. Or three branches, but it's directed only one way. You can't do a cycle. Oh, okay. So, and then you go, oh, we want to do a cycle. Oh, okay. Well, that's called a graph. So that's not a tree anymore. That's called a graph, even though you got two here and two here and two here and one here. Okay, and this other one's null. Okay, this is not okay. You need for this to be a graph. You'd have to put one more node, one more edge here, or one more connection between Jan and Alice, and then that would be a graph. So he's not really. I mean, okay, you got two coming in here. I mean, sort of, maybe. I have to look at it again. But that's all it is. That's all it is. There's nothing. There's nothing magical about this stuff. That's it. And these are so each value has a pointer to two. Ooh, okay.
don't do anything by themselves. A graph has a node for the data and an edge for the relationship.
Okay, edge, connection, whatever the hell you want to call pointer. Okay. Wow. Could you put more names on stuff, guys? Thanks.
Between the data points. Data structures are essential, but they don't do anything by themselves. To do something useful,
okay, edge, pointer, connection, node, value. Okay.
you'll need to code up an algorithm, which is just code that solves a problem.
I took the initiative in creating the internet.
In our code, we
created it.
have several mechanisms for implementing algorithms, the most fundamental of which is a function, which is a block of code that takes an input, then does something, and returns an output.
Right, so the inputs are here. So you bring in 1 and 2, then it says, oh, okay, put it in the ALU, put it in the computer, go to the thing, then give me the answer back. It says, oh, this is just 3. So I return 3. So whoever called this gets an answer back 3. That's it.
Like a variable, a function has a name, and it can be called from other parts of your code with different input parameters called arguments. One thing you might do in the function body is compare one value to another. Every language has a variety of built-in operators like equality, greater than, and less than that you can use to compare two values.
Right, so this is different. This operators is different than the opcodes. It usually just means greater than, less than, multiplication. They sometimes, some languages say, okay, that's not, the multiplication is not an operator. Someone says it is an operator. So it really depends on the implementation of the language you're in. But for the general case, yes, greater than, less than, equal to, greater to, less than, and greater to, all that stuff. Those are operators.
Operators like equality, greater than, and less than that you can use to compare two values. If A is greater than B, then it forms a value of true. But if B is greater than A, then the value is false. True, false is what's known as...
Right. So it compares these two and returns it here. So this will be a true or false over here. That's it. The only two states it can be, true or false. It can't be indeterminate. It can't be unconnected. It's always true or false.
As a Boolean data type. And whenever your code produces a value like this, it's known as an expression.
Right. This equals sign here. Signing this, whatever the value of this thing is, it's an expression. So whatever this is, and then you get to assign it a value, even if the value is 0 or null or -1 or whatever. That's called an expression. Versus like a command. If you say if A is greater than B, that's sort of like a command. That's not what that's. There's no resulting value, but there is a resulting value, isn't there? The comparison, isn't that a resulting value? In my mind, it is, but these guys are like, no, that's different. It's like, all right, whatever.
But not all code will produce a value. Sometimes your code will simply do something, which is known as a statement. A good example is the if statement, which handles conditional logic.
But isn't that's what I'm just saying? Isn't this getting a value? The value of true or false? All right, whatever.
For example, if the condition is true, it will execute this code. Otherwise, it will short circuit and run the code inside of the else block. Another very common type of statement is a loop. A while loop will run this block of code over and over again until the...
Yeah, they use this thing while, and all they're saying is, while this is true, keep doing whatever's in here. Oh, wow. Gosh, guys.
Condition in the parentheses becomes false. That can be useful, but more often than not, you'll want to loop over an iterable data type like an array.
Iterable. Ugh. Hey, this is more math words. It just means you can count. It has you can say, "Give me the next one. Give me the next one. Give me the next one." That's all it means. It means that when you give an array with this value, you can say, "Give me the next one." Wow, it's an iterable. Okay.
Languages have a for loop that can run some code for every object in the array or iterable data structure.
For loop. I hate this for loop. This came from Fortran. This should just say loop here. Just instead of saying, just say loop n. So n means use this variable n as the counter, and every time you go up for each value for each for n and num, so there'll be 1, then 2, then 3, then 4. So it says no. So use nums as the source of the number of things to loop over, and then each time you get that, you pull the n out and use that as the here's numbers for m's. If the first one's here, use that, print it out, print it out, print it out. That's all it is.
Now,
so
in some cases,
so I wish it would use. This is a leftover from C. So all these languages we're using are all Kernighan, Ritchie, Dennis Ritchie, Kernighan, Ken Thompson, Dennis Ritchie and Ken Thompson. Those two guys, Kernighan, Ritchie, those guys, Dennis Ritchie and Ken Thompson, those guys. We're still using their stuff because they were so influential. They were like the first that really kind of like nailed down some of these concepts and just standardized some of this stuff. So thank you for doing that, but this should say loop.
A function may not have an output, which is generally called a void function. An interesting thing about functions is that they
void. Void just means nothing, null, zero. Nothing, null, zero, empty. Whatever. -1 doesn't exist. The idea of doesn't exist or doesn't return anything. It's also called, what do they call it? Unit. They call it unit. How about nothing? No, that's too much typing. We gotta call it void. He did talk about this. It was kind of like a fun thing for him because he was kind of a sci-fi nerd. So the void, it returns nothing. It returns the void. Super confusing. Funny as hell. It's like inside humor. The void, we return nothing. Very dramatic.
A void function. An interesting thing about functions is that they can call themselves. When a function calls itself, it's called recursion, because when done like this, by default, it will recurse forever, creating an infinite loop. That happens because when you call a function, the programming language will put it into memory on what's known as the call stack, which is a short-term chunk of memory for executing your code.
It's just a little piece of memory with a pointer to it. Oh, there's the stop. Okay, put something on top. Oh, there it is. And all you're putting on the stack is just the parameters of wherever you were at last. So when you come back, after you're done wherever you're at, when you come back and pop, you get all the values back. Ooh, the stack. What else do they call it? What else do they call it?
Because when done like this, by default,
recursion. You mean looping around itself? Okay.
It will recurse forever, creating an infinite loop. That happens because when you call a function, the programming language will put it into
a short-term memory. No, it's just memory. I mean, there is one inside the CPU usually. They'll have its little stack pointer for its own internal stuff that it does. But that's usually somewhere in memory because if you have a really large call stack like a recursion, you can't put this in short-term memory. This has got to go in RAM. So when short-term memory, I'm not really sure he's talking about here. It has to go in memory. It has to go in regular memory with everything else.
Memory on what's known as the call stack, which is a short-term.
Yeah, the call stack. So when you call a subroutine, when you call a little subroutine, it pushes whatever the values are where it just saves its state and with just a bunch of numbers, and then it pushes it onto the memory. And then it jumps into wherever it has, and you can fill up new stuff. And then when it comes back, it just pops this off.
For executing your
pops this off like a plate and says, oh, this is where I was last. Okay. And it's super simple. Like, whoa, they made such a big deal about this. And it's not. It's just real simple, super basic concept.
So when a function keeps calling itself, the language will keep pushing frames onto the call stack until you get a stack overflow.
Frame. So all the values, so the chunk of values, the state of the program, wherever it has with all the variables, wherever it was at that time, that's called a frame. A frame. Oh.
Error. To avoid this, your algorithm needs a base condition so it knows when to terminate the loop. Now, when you write an algorithm, you'll need to determine if it's any good, and the system for doing that is called big O notation. It's a standard format.
The big O. Get it? You get it, big O. Computer people are funny as hell. All this means is how long is this going to take, man? how long is this algorithm, given how it operates? How long is this going to take? That is all we're doing. Is it going to be done in our lifetime? I mean, lifetime of the universe? Is it going to be done in our lifetime of our great grandchildren? Is it going to be done in possibly a lifetime of me? Is it going to be done this week? This week? Is it going to be done today? Is it going to be done right now?
For approximating the performance of an
That's it.
algorithm at scale. It may reference time complexity, which is how fast your algorithm will run, and space complexity, which deals with how
Space complexity. Time complexity is just how long is this thing going to run? How complicated is this thing? The complexity of it. More of this math terminology that's super confusing. It's because the math people love it, and they actually know what all this stuff means. It is useful to have these terms, but when a newcomer comes into this, someone comes, it's like complexity. What are you talking about? They're just talking about how long is it going to take. How difficult is this problem going to be with all the loops, and how many time cycles is it going to take to make this happen?
the performance of an algorithm at scale. It may reference time complexity,
And they call that time complexity. Okay.
which is how fast your algorithm will run, and space
And then
complexity,
space complexity is like if you do recursion, it has to go loop on itself, and has to put a new frame on the stack each time. Well, that space complexity is going to get really huge if you keep going with that. If that recursion is super deep, you're going to run out of memories. That's your space complexity. It's so silly.
which deals with how much memory is required.
I mean, it's useful as hell to know about this, yes. But the big deal that people make about it is a little bit much.
To run it. Developers have many different algorithm types at their disposal. The most crude option is brute force, where you might loop over every possible combination to hack somebody's credit card.
Right. So this one would be ON. Okay. Brute force on this particular one is ON. And it's 10,000, so it's going to take, however many times you can switch that wheel times 10,000. ON.
Pin. A more sophisticated approach might be divide and conquer, like binary search, where you cut the problem in half multiple times until you find what you're looking for.
Well, if you know what you're looking for. If you know the answer, sure. Yeah, if you know the answer already, if you know what you're looking for already. But in the case of that brute force search, that's not, no. I mean, that's sort of a way to think about it. But if you're, that we don't know what we're looking for yet. In the case of that thing, if we knew the combination was 50 and we could only flick up one at a time, am I at 50 yet? Am I at 50 yet? Am I at 50 yet? Am I at 50? Yeah, that's kind of how they're the similar idea. Am I at 50 yet? Because the computer will going to see one thing at a time. Am I at 50 yet? Am I at 50 yet? It doesn't know to jump. Unless you use this divide and conquer that goes, okay, if all those numbers are in sequential order, all right. So I can just see if this number is the value. No, okay, jump to the middle. Oh, there it is, 50. Okay, there you got it. Or if it's the number's 38, it's like, oh, let's jump to the middle. Is this one 38? No. Okay, let's jump to the middle. Oh, is this greater than? Is the middle one greater than or less than 38? Okay, then it's down here. And then do that. That's divide and conquer. Okay. They make these terms up, and it means something very specific. When you understand, it means dividing the problem in half space. Log squared, whatever the hell. They're just talking about the same stuff.
For. Another option is dynamic programming algorithms, where a problem is broken down into multiple smaller subproblems.
Log in problem. I always get the terms mixed up because it's silly. It's like, okay, I mean, it's almost barely worth talking about because you're usually not implementing these algorithms. I mean, you can mistakenly do it sometimes, but if becoming aware that you should be using libraries for a lot of this stuff, you shouldn't be rolling your own because of these type of issues that show up immediately. Unless those data sets are really tiny, like on UI stuff, it's like the data sets are tiny. We're sorting 100 items. We don't have to worry about it. Now, if we're sorting 100,000 items, okay, first of all, why are you bringing that down to a little device? Or, now the devices are fast enough that bring it 10,000 down. It doesn't, so what? We don't care. It's fine. If it's 200 million, okay, well, that's different. Why are you bringing 200 million records down to your device to have it sort? That's kind of silly. So it's like that level of awareness. Like how much are these devices capable of? And this is the kind of stuff you have to know about. But people get a little too obsessive about it.
And the result of each computation is stored for later use, using a technique called memoization. That means if a function has already been called, it will use the existing value.
Oh, so if you already know, if you have so you just keep a record of what's been already calculated, and if value comes in for the same key, if you bring in a 2 and you already calculated it once, you just go look it up. Oh, wow. Revolutionary, guys. Revolutionary. Wow.
instead of recomputing it.
So, and then you compute it if you haven't looked it up yet, and then store it for the next time. Wow. Revolutionary. Memorization. Wow. That's really beyond amazing, guys.
Again from scratch. Then we have greedy algorithms that will make the choice that is most beneficial in the short term without considering the problem as a whole.
Okay, that's all this algorithmic corroborating stuff, which if you are approaching if you have a problem that you need to learn about these greedy algorithms, you'll become aware of it. It'll become an issue, and you'll actually know, and you'll go look into it, and you'll learn how it's applied. Other than that, you don't have to know about that stuff.
Example of this is Dijkstra's shortest path algorithm.
I mean, are you going to implement Dijkstra's in the interview? And if you are, why are you working at a company that wants you to learn that level of stuff when there's way more important stuff? This has already been implemented by this gentleman. There's libraries you can contact. There's actually Google libraries that will let you try from one to the other. Why are you trying to implement Dijkstra's? It's good to know how it works. But if you're trying to implement it you're using that part of your brain you need to know how it works. As soon as you know how it works, you can let it go. It's like, okay, this guy is 140 IQ genius. He figured out this way to do it. It works 99% of the time. That's all you need. And then, so after that, use Google or use some other map libraries program. You know what I mean? It's like, you don't want to implement this stuff. You want to be the next level up. You want to use these guys. Excellent, groundbreaking work. Very clever, but you don't want to be the one implementing it. No. Mm-mm.
On the flip side, we have backtracking algorithms, which take a more incremental approach by looking at all the possible options, like a rat in a maze exploring all the different potential paths. Now, when it comes to implementing,
good to know how that stuff works. Again, good to know how all stuff operates once. But if you stick in that neighborhood, I mean, there's just libraries that can do all that stuff. Once you know how they operate, go use the libraries and forget about the implementation details. Not important. I mean, you can do it as a hobby, I guess, but this is pointless area. You just gotta know how it works to move on.
In your code, there are always multiple ways to get the job done. One programming paradigm is declarative, where your code describes what the program does and the outcome, but
Right, HTML.
doesn't care about things like control flow.
Declarative. Declarative. Yeah, I mean, Compose, which I love, is a graphics library. It is declarative, but it's like you're just writing commands. It's okay. What are you talking about? Like, it's these delineations between these things get kind of fuzzy for me, and people make a really big deal about making this. This is important. This is declarative. This is imperative. And this is functional. And it's like, it's all kind of blends together, man. It's all just code running at the machine down there. It's how we conceptualize and look at it. We're gonna split this problem up. One side's gonna be functional. One side's gonna be imperative, and the other one's gonna be procedural, and the other one's. You don't have to pick one. You can blend them all together. It's all just code at the bottom. So
this style of programming is often associated with functional languages like Haskell. The other paradigm is imperative programming, where your code uses statements like if and while, providing explicit instructions about.
Right. So you're just being so we're gonna get into this style, what's different about it, but it's still just doing the for at its bottom. It's just doing imperative stuff. So what are you talking about? Okay, this is kind of declarative. Okay, we're declaring a loop here. We're not actually saying how the loop works here. We're just going to make sure, just know that if you put an I here, we're going to increment it right here. But we're not going to do the thing. It's just going to do the thing. There's a way to do it. They had goto in C. You could actually put a goto here and put a label here and do it just the old way. But we're going to make it declarative. Okay. I mean, it's just kind of splitting hairs there a little bit.
About how to produce an outcome. It's associated with procedural languages like C. Today, most general purpose languages like Python, JavaScript, Kotlin,
procedural, I mean, C is just structural. We'll get into it.
Swift, and so on are multi-paradigm, which means they support all these options at the same time. In addition to object-oriented programming, the idea behind OOP is that you use classes to write a blueprint for
This is class. I call this class-oriented. So this is not OOP. This is class-oriented programming. And the guy, Bjorn Strustrup, whatever the hell you pronounce it, the guy that created C++, who they get all these ideas out of, and Python was a derivative of, and Java derivative of. He said, this is not the object-oriented. This is my thing. That C with classes really was more appropriate, honestly.
The data or objects in your code. A class can encapsulate variables, which are called.
But he wanted his. But he's a marketer. He wanted his. So right around the time that he was doing his stuff in '79, the object-oriented stuff that Alan Kay was talking about was coming through. But Alan Kay wasn't able to make it practical for people. So what happened was Bjorn took those ideas, some of the ideas, and applied them from what his work in Simula. He listened to a little bit and he brought up the hype wave of this object-oriented stuff. It's like, well, I'm using objects. Well, not really the way Alan Kay was talking about. So he co-opted the term. He co-opted the term and he's like, I didn't mean to do that, but it just happened. Oh, come on now. His stuff was useful for the time and it is still useful today, but it's bloated and it's beyond. So the way that idea, yes, you get the maximum screaming performance out of it. But for most cases, we don't need all that performance now. These machines are fast enough. We don't need to do all that stuff. For most most applications, you don't need to do that stuff. And honestly, it's a lot of hassle and trouble for just a little bit of bang. And sometimes you need it, but most of the time, no.
Commonly called properties, as well as functions, which are usually called methods in this context. It's a common way.
Yeah, method is just a function. Method is just a function. It's like keep you rewriting these words. A method is just a function that happens to be inside of a context of a class. Okay. Which is just a data structure. Okay. Jeez.
Way to organize and reuse code because classes can share behaviors between each other through inheritance, where
Oh, God. This one. We'll get
a subclass can extend and override the behaviors of the parent class, and it opens the door to all kinds of other ideas called design patterns.
Yeah, bad ideas.
Now, a class by itself doesn't actually do anything. Instead, it's used to instantiate objects, which are actual chunks of data.
Okay, so this is allocate memory for this variable and a pointer to it. Oh, wow. And instantiate. People, I actually had arguments with people saying, isn't it just allocating a struct and pointers to functions? No, it's instantiating an object. I mean, it's just allocating memory and just filling it in with the variables inside the struct. No. It's creating a constructor. It's like, and then I find out later, no, I was right. I was right the whole time. And these guys were just being jackasses, and I don't know why. But I was right. It's just allocating memory and initializing a variable, setting a variable in memory. Oh, wow. Let's instantiate an object of a class
that live in your computer.
Stop, guys!
Often, you'll want to reference
this stuff is so off-putting.
The same object over and over again in your code. When data is long-lived, it can't go in the call stack. Instead, most languages have a separate area of memory called the heap, which unlike...
Okay, the memory? You mean memory that has pointers to it somewhere so you can shuffle it around? These terms are just so... it gets a little annoying.
The call stack can grow and shrink based on how your application is used. It also allows you to pass objects by reference, which means you can use the same object in multiple...
Oh, you mean a pointer? Oh, you mean a pointer? Oh, no, it's a reference. Oh, you mean a pointer? Well, I don't know why they keep doing these things. You're passing around a reference. You mean a pointer? No, it's a reference to a variable. You mean a pointer to a memory location? I would actually say this stuff and not making friends, but also kind of over the bullshit. It's like a little off-putting. And I like to seek the truth. I don't care if who's right or wrong. I don't give a fuck. All I want to know is, like, is this really what I'm looking at? Is this the same thing as this? Are you guys have you guys succumbed to the marketing that I've been looking at since I was age 7, seeing the hype waves and actually seeing the results? And it's just like, it's not the hype, man. And these people would argue with me about this, and I was just like, no, this is not what's going on. And I eventually just kind of gave up and was like, realized like, oh, I have to go look into this stuff myself. And just when somebody's like, no, it's this, it's that, they've bought into some marketing hype. And sorry, I can't really. We're not going to be friends because I'm not going to be able to talk to you because I'm looking for the truth, and I want to get to the bottom of things, and I want to use these things to make something else other than just knowing the latest lingo. No, I know the lingo. You have no idea how much lingo I know. Oh, it's just a pointer? No, it's a reference.
Variables without increasing the memory footprint.
Look, you have a pointer here.
Because it always points to the same chunk of memory in the heap. Now, what's interesting is that if we go back
in the heap, it points to reference in the heap. Oh, memory location. Oh, okay. These guys.
That we talked about in the beginning, you'll notice that it contains multiple threads. A thread takes the physical CPU.
A thread? You mean where the program's currently running? The memory locations, where the thread of execution, when it jumps off, it's over there, it's over here, it's over there. It's a thread. It's running on a thread. Oh, it's just where the CPU is just running in that location? No, it's a thread and it's a process. It's just code running and branching and running and branching and where it's going. It's one CPU doing its thing. If you have multiple threads. Well, I mean, one CPU could be split up. It could do sharing with software. It'll split it up. They have multiple threads of execution. It's like, okay, just flipping, flopping between, okay, I'm on, executing code here. It's like, oh, the operating system says, well, pack everything up, put it on the stack, flip over here, unpack everything, start executing where you were before. Oh, it's getting stuck now? Okay, pack it up here, flip back out the other thing. That's it. The thread, the execution of a thread. It's ridiculous.
And breaks it into virtual cores that allow it to run code simultaneously. There are some programming languages that support parallelism, where you can write code that literally executes on 2 different threads at the same time. However, many languages...
No, if you have 2 CPUs, yes, it'll operate at the same time, because each one's running in a different, each one's going up with the code of a different area. But if it's one CPU and 2 threads, it's not doing it at the same time. It looks like it is to our perceptual levels, but underneath it's just going to one area of execution. The operator says, okay, stop there, pack it up, place all your stuff on the stack, go over here, replace the stuff that was there before, and start running this code over here. It's not running at the same time. It looks like it is to us. It's not running at the same time. So it's a little bit, so there's a lot of this kind of like languagey, little loosey-goosey, not quite understandy-wandy, how things worky, lingo. I'm important. I understand a thread.
Out there are only single-threaded, but that doesn't mean they can't do 2 things at the same time.
No. It's only one thing at a time, sir. It looks like it's doing 2 things at the same time. It seems like it to the user, but under the hood, it's still only ever going to do 1 thing at a time per CPU. Let's just talk about 1 CPU. It'll switch back and forth, 1 thing to the other, real fast, so you can barely even tell. But it's not at the same time.
Instead, they implement concurrency models like an event loop or
concurrency model. You mean things are working in parallel? Stop. Or it looks like or we can simulate it. We can make it seem like it. So with one thing's waiting, it'll do something else until that thing's waiting and it'll do something else. So it's never really waiting just anywhere. Like in the old days, it would just sit there and wait until the next thing. So we gotta figure this out. We can't just wait here while something else could be happening. It's just waiting there. How can we make that? Okay, we'll do a scheduler in the operating system. It's like, well, if it sees it's detected, it's halted, or the software says, I'm going to wait here now. They're like, okay, time to switch the thread. It just saves this current parameters on the stack, switches over, starts over where it was before, some other location or some other program. And if there's no other program, it just waits there. That's it. Concurrency model.
coroutines that can pause or delay the normal execution of code to handle multiple jobs on a single thread at the same time.
Same idea. Just one's built into the language, one's doing it by the OS. Okay. Same idea, where it stops one, saves the state, pops over, starts over again. Saves the state, pops over, goes again. Same shit.
In modern computing, we're rarely working with the bare metal CPU and RAM. Instead, we work in the cloud with a virtual machine, which is just a piece of software that...
It's the virtual machine. I mean, it's just an emulator. It's a software running another simulation of hardware. So anything in software can be written in hardware. Anything in hardware can be written in software. The reason why we simulate it in software is because we don't want to build it in hardware. We're going to pay extra time, the time cost, because it has to be emulated. You're running a little miniature program that simulates a CPU. Ooh, virtual. It's virtual. You don't know because it's virtual. I mean, it's just emulated, just running a piece. It's running another program that runs a program that runs a program. Okay.
That simulates.
No, it's virtual. It's different.
It's hardware that allows us to take really big computers and split them up into a bunch of smaller virtual computers. These machines are the backbone of the internet and are connected via the internet protocol. Each machine has a unique IP address to identify it on the network.
Just like a memory address. It's very similar idea. No, it's not. It's different. No, it's like it's like a graph network. Everything has an address, just like a memory cell. It's the same thing. Don't think? No, It's an IP address. It's internet protocol.
IP address is usually alias to a URL that is registered in a global database called a domain name service. Now to
URL, universal resource locator.
it on the network, that IP address is usually alias to a URL.
This is a key, right? This fireship.io is a key, and the value is some IP address in some database somewhere. And they figured out how to do this in a way that scales pretty okay, sort of, mostly. It's good enough for now. But yeah, key value in some domain name service. It just doesn't look up. Oh, if it's IO, it's going to be this server. It's going to be com, it'll be this server. Oh, it's Fireship. Let's go F. There we go. Fireship. There it is. There's the IP. Here's your IP address. Universal resource locator. You mean an address? Oh, you mean like a key to an address? Oh, wow. Amazing, guys. Thanks for that insight. No, it's not an address. It's a universal resource locator.
That is registered in a global database called a domain name service. Now, to establish a connection, the two computers will perform a TCP handshake, which will allow them to...
A TCP handshake. Oh, you mean like a just protocol? Like, okay, I'm about to send something. Really? What are you going to send? I'm probably going to send this. Okay, we'll send it. All right, I'm ready.
exchange messages called packet.
The TCP protocol, transport control protocol. Which is the transport? the bits coming off the wire. That's the transport. What's a packet? You mean little groups of bits are just coming along on the wire as it wiggles on and off? 8 at a time, or 16 at a time, or 256, or whatever the packet size is. How many bits at a time? That's it. A packet. Oh, it's number of bits. In a group. In a data structure, you've done some standard you guys have decided arbitrarily. Oh, a packet. Ooh, a packet. Ooh.
On top of that, there's usually a security layer like SSL to encrypt and...
Ooh, a SSL. So you're using some math, some cryptographic stuff that some geniuses figured out to exchange private information in public. That, it's cool to know how it works, but it's like, okay, after that, it's like, okay. It does a little interchange, and this all happens behind the scenes. It's like, it's good to know how it works. But are you actually involved with making SSL code? No, we use a lot of libraries, and you don't want to mess with that stuff. Anybody goes, we're going to roll our own cryptography. Run.
decrypt the messages over the network. Now the two computers
You're about to get hacked.
can securely share data with the hypertext transfer protocol. The clients may...
Hypertext transfer protocol. Oh, it's just saying, okay, I want to get this page. Give me this. Send this command to the server. Give me this page. And he goes, okay, looks it up on his page list. Oh, here's the page. HTT, hypertext transport protocol. It's just some words and commands people made up and decided this is how we're going to do it because everyone's doing it their different way, and we're never going to scale without having some kind of standard. Okay. They were already doing this stuff way before the HTTP protocol became standard. But once it did, we were like, okay, we're just going to use this now just to get data back and forth and have a standard way of looking at it. All right. Constantly doing that.
Request a web page, then the server will respond with some HTML. Modern servers provide a standardized way for a client to request data, which is called an application programming interface, or...
Ooh. Oh, you mean this is another protocol? It's like, I'm going to send these sets of commands to you, and you can send me this sets of data back? Ooh, it's an API. No, it's not a set of list of things that it can do and data will return. It's an API. Application program interface. I mean, it's just a set of things you've decided on. If I send you this, you're going to send me back that? Wow, guys. No, it's an API.
Or API. The most common architecture is REST, where URLs are mapped to different data entities.
REST, representative state transfer. Oh, it means that if I ask for this data, you're going to give it back to me? Wow. So if I create a document, if I give you a command to create a document, you're going to go create that document. And if I ask for that document back, you're going to give me that data back. Wow. If I update something, I change something, I'm going to update it. And if I ask you to delete it, you're going to delete it. So you're going to create, read, update, delete. You're going to CRUD. So you're going to let me do those commands. And that's going to be a representative straight state transfer. Haven't we been doing that the whole time? No. Rest is different. It's a standard.
entities available on a server. And that brings us to our final topic, mother effing printers. You're going to need to learn how these things work inside and out, because every time you go to grandma's house, she's going to ask you to fix.
Yep. Well, those days are kind of ending now. They're starting to be, can you get my VR headset? Girlfriend hooked up. My boyfriend, my VR boyfriend needs updates.
Which shouldn't be a problem for a computer scientist like you. Thanks for watching, and I will see you in the next
All
one.
right, that's an hour of me ranting.
What's the first thing you should do when you're
That's enough of me ranting about that. We're gonna continue on. The next section is gonna be on numbers, and this one you gotta know about. Negative numbers in computer science, two's complement. You have to power through that one, and it is important to know how it works because it's like super clever and lets you know how things are underneath the hood, especially if you start looking around at it. All right, we'll continue that next time.